Hi everyone. So in today's class we'll be teaching circular motion. Let's start with the question, what is circular motion? Now circular motion is the motion of an object that follows a circular path. So if an object is found to actually take the whole path of a circle, the object is said to have undergone circular motion. Now an often confusing part, there's a particular motion that people always tend to confuse with circular motion, and that is rotational motion. For rotational motion, is only the extreme end of the object that follows the circular path, not the entire object itself. So take note of that. That's the major difference between circular motion and projectile motion. For projectile motion, what am I saying? That's the major difference between circular motion and rotational motion. For rotational motion, usually the extreme ends, like the rims of the objects that follow the circular path, while for circular motion, the entire object follows that circular pathway. So that's the major differentiation between the two of them. Now, circular motion can either be uniform or non-uniform. Now, during uniform circular motion, the angular rate of rotation and speed will be constant, while during the non-uniform motion, the rate of rotation keeps constant, it keeps changing. So anytime you're referring to something as uniform motion, non-uniform motion, you are referring to what? To this velocity, basically. Now, some examples of circular motion is that of the satellite, man-made satellite around the Earth, and that of the moon too, moving around the Earth. That's also an example of circular motion. And circular motion, now I think they've started mixing circular motion with that of rotational motion, as I said before, because they're saying something about the blades in a wind turbine. Okay, the blades in a wind turbine are following circular motion. Yes, yeah. And then the wheels, any point along the so let's say you have this tire here. So this part of this tire will move around when an object is moving, is when the car is moving. So that particular aspect is the part that actually undergoes circular motion. Okay, now a particle is said to execute circular motion when it moves along the circumference of a circular path. And an important aspect of circular motion is that the direction of the motion is changing continuously, unlike in the case of linear motion. Now, what they are saying here is that you have circular motion, you have a circular path, the object is undergoing the circular path, and now when the object is following a circular path, there will always be a center of the circle, there will always be radius of the circular path, and all. So let's start with this now. You have the radius of the circular path. Now what they're saying is that all along the line, as the object is moving in this circular path, the velocity, the direction is always changing, because the normal direction was in this way before, then it changes to this. So the direction of the object is always changing in the circular, when an object is undergoing the circular motion. So now, since you are dealing with the circle, that means the object will have what? An angular variable. So for every linear stuff we have the angular stuff as well too. So let's talk about some of the variables now. We have the angular displacement. We have angular displacement. We have angular velocity, and yeah, and then we have angular acceleration too. So, but before we talk about angular acceleration and the rest, let me quickly explain angular displacement, angular velocity. So now, since I said before that the object is following the circular path now, so it will have the circle will have a circumference. We have we have a radius, we have a center, and we have the circumference. So now let's say the object goes to this point. So from here to this point now. Now the angular displacement is the angle suspended at the center of the circle when the object moves along the circumference of the circular path. So this here is the angular displacement. Now the circumference covered when an angle is suspended at the center of the circle of the circular path is the linear displacement. And the difference between your linear displacement and your angular velocity and your angular displacement is what? S equals what? Theta r, such that what? Your theta is equal to what? S over r. S is what? Circumference now, so you have what? 2 pi r all over r, so that your theta is what? 2 pi. Now the unit of angular displacement is what? Is radian. Take note of that. Let's go back. Oh, let's talk about velocity as well, to angular velocity, angular speed, angular velocity. Now for every angular, you have angular displacement, you have angular speed, and we already said before that the direction is always changing, so that means there will always be what? Changing the velocity. So to calculate the angular velocity, now it will be what? Angular velocity is usually with what? Omega. So you have omega equals to what? Change in what? Theta all over what? Change in time. While your linear velocity will now be what? V equals to what? Change in linear displacement all over what? Change in time. Now you can replace your theta with what? S over r, so that you have what? Change in S over r divided by what? Divided by your t, so that you now have what? Change in S over change in time times r. Change in S over change in t is what? Is what? Your linear velocity. So you have what? Your omega equals to what? V r. So that's for your linear, your omega, the difference between your angular velocity and your linear velocity. Okay, these are basically every single thing I've said. And then the unit of your angular velocity is what? Rad per seconds. While the unit of your linear velocity is what? Meter per seconds. It remains, it retains that. Well, let's talk about this relationship. Now, another thing you should take note of is your tangential acceleration and your radial acceleration. Your tangential acceleration is the component of the acceleration of the object, or the velocity, that is in the same direction as the velocity of the object. So take note that as the object is moving now, this is the direction of the velocity of the tangential of the velocity of the object, of the linear velocity of the object. This is the direction of the linear velocity of the object. This is the direction of the linear velocity of the object. So this, all this, and another name you call linear velocity is what? Tangential velocity. Take note. Take note of that. Is what is tangential velocity. So for tangential anything, you have tangential acceleration. Like basically, these things are actually like very straightforward. Once you have angular velocity, angular acceleration, you use angular velocity to calculate what? Angular acceleration, or this way. So that's why the acceleration in this direction also refers as what? Your tangential acceleration. And you can always calculate it with what? Using what? Your tangential velocity or your tangential acceleration. And then you now have what? Your radial acceleration. Now radial acceleration is the acceleration that is keeping the object from moving away from the circular part. So your radial acceleration, is always directed what? Is always directed in this direction. So your radial acceleration can also be referred to as your centripetal acceleration, actually, because to calculate your centripetal acceleration, your centripetal force, you use what? Your radial acceleration, and centripetal force, centripetal acceleration. And for calculating your tangential, let's start with tangential acceleration. Tangential acceleration is what? V1 and V2 minus V1 all over what? Change in time. Why for your radial acceleration, it is what? V square over r is also equal to what? Omega square r. There's a way to derive this thing, but I don't think you will be asked for derivation. You are writing, you tell me. You will be asked to derive it. So that's what? Your tangential acceleration and your radial acceleration. Take note of those formulas. Now every single formulas I'll be giving you, take note of them. Now you might not really get the way I think you should be able to even understand the way I get some of these formulas. But then the important part is for you to know the formula, to be able to relate with the formula. So that when you are solving questions, you'll be able to like, oh, yeah, this is the formula I should use for this thing because these are present in internal accountants. So take note of all those formulas. Okay, basically what I've just said before. Now let's talk about your angular acceleration. Now angular acceleration is just a rate of change of what? Your angular velocity. That's it. As simple as that. So that will be what? Your angular velocity over what? Over your angular, over your time, basically. So let's continue. Now circular motion can be uniform and non-uniform depending on the nature of the acceleration of the particle. Yes. Now the motion is said to be uniform when the particle is moving along a circular path possessing a constant speed. Now the speed or in a circular object, in an object following a circular path, will always be constant. The only thing that is always changing is what? Is the direction. And when the direction changes, it changes what? It changes the velocity. That's for but then the speed is always constant, whether the circular motion is uniform or non-uniform. Now, for non-uniform circular motion, the okay, let me just now the motion is called circular motion when the particle is moving along a circular purpose, let's say a constant speed. Now during circular motion, the velocity vector changes its direction. I just said that before. Like direction changes at each point on the circle. As I drew here, like the direction is always, the velocity is always changing. Like the velocity vector is always changing at every point in time, every point, just so as make sure that the object is following the circular path. Negative. Now this implies that the radial component of the acceleration is always non-zero. Yes, that's very true, because in order for the object to keep changing its velocity every single time, there has to be something that is preventing it from just following its own path. Because normally the body just wants to just be going, it just wants to be going in this tangential direction. It just wants to be going. It wants to be going. Just wants to be going in this direction, just wants to be going in this direction, just wants to be going, just wants to be going, just wants to be going. But then this acceleration is just pulling it back. You don't go anywhere. You're not going anywhere. You're not going anywhere. All along the journey, it keeps pulling it back. Keeps pulling it back. Keeps pulling it back. But then it doesn't stop it from actually attempting to like go out. So that's why the radial acceleration is like very, very important. Both the radial acceleration and the tangential acceleration are the two accelerations that maintains the body in a circular motion. Now, the tangential component can take a positive or negative value in the case of non-uniform circular motion and a zero value in the case of uniform circular motion. Now, when I said that the acceleration of a particle in the circular motion is always directed towards the center, it's given by v square over house. I did give that. That's the radial acceleration, and then your centripetal force now. Based on Newton's second law of motion, what Newton's second law of motion states, he says that what the rate of change of momentum is proportional to what? To the velocity, to the force applied. So that is what they did here. So we have our acceleration already. So we just added what? Force is equal to what? Force is equal to ma. So A is equal to what? I say F is equal to what? Me. So that means what? Your F is equal to what? Mv square over r, or m omega square r. And that F there is what? Your centripetal force. And your centripetal force is also referred to, your centripetal, the radial acceleration is also referred to as your centripetal acceleration as well. So that's basically what I just this is basically what we just talked about here. That's the diagram to represent it, to illustrate it. Now, example of body that has centripetal force is what? The gravitational force, and then the string, the tension in the string, when you have a string, when you attach more like a bulb to a string, and then you start wheeling it around in a circular path. That's an example of because there will be a force that will be pulling it towards the center and all this. Okay, now moving on. Let's talk about application of Newton's law of motion with respect to circular motion. This is very important because this is more like an application part. These are the areas where they will start asking you questions. Now, the application of Newton's law of motion with respect to circular motion has two aspects. You have the level road, and then you have the banked road. Now, banked road is just more like an elevated road, something like this. Now, this is level road. Then banked road is like inclined at an angle to the horizontal, like. Now, there are three major forces that we should take note of when we are trying to talk about all this. We have the weight of the car, because we are dealing with a car now. We are dealing with a road now. Is that car or motorcycle? Without the two. You have the weight of the car or the motorcycle. You have the frictional force, and then you have the normal reaction. Now take note that in the vertical direction, for a normal road, in the vertical direction, your normal reaction is always equal to your weight. Now your weight is the one that leads to the reaction from the ground, so it has to be equal to it. Now take note that your weight can be greater than the normal reaction that the ground can exert. Now if your weight is greater than the normal reaction that the ground can exert, then you start to like drown into the ground, like you start to go down, or the surface in which you are supported, in which the car or you are being supported on will break. But it is not possible for the normal reaction to be greater than the weight of the car, to be greater than the weight of the object that is resting on that surface. So just take note of that. There is limit to the normal reaction, and all this is related to what, to stop being static. That's when the stop is static. You have your new to be equal to what, mg. Now, so on level road, the friction holds back the vehicle from moving away from the circle. So when you're trying to like make a U-turn, it's the frictional force that prevents the vehicle from actually swinging away. That's why most of these cars that always tend to like drift, if they're trying to drift on a icy road, they will just be going, because they won't be able to like make that turn, because the friction on that ground, on that icy road, is close to zero. So frictional force. So since we said that the frictional force is the one that is maintaining the what's called that is keeping the object in the circular motion. That means it's the one acting as the centripetal force. So that we can say that the frictional force is equal to what, mv square over r, which is also equal to what, nu n. So that the coefficient of friction now becomes what, that means our speed now v now becomes what, square root of what, nu rg. Let me try and derive that. At least that's something you can, in case you forget, because I think this aspect are always the areas I tend to forget during that time, like when I was like the first few, like probably the first 2 times I wrote UTME or so. So you have your frictional force to be equal to mv squared over r, which is also equal to nu n. So that means you can equate these two together, so that you have what, n, nu n is also equal to mg. So m cancel m, so you have v square over r equals nu g. So v equals what, nu gr, square root of nu gr. So that's it. This is your v max. That's the maximum speed required for the object to actually make this successful turn around the roundabout. So let's talk about bank angles. That's those ones that are inclined, like they are elevated. Now the ground is always elevated at a particular angle to the horizontal. So you have that to be what? To be your theta here. And you have your normal reaction also. There will always be normal reaction, there will always be weight of the object. Yeah, there will always be friction. Now imagine this. Now you have an inclined object. Now you are placing an object on that inclined surface. The object will want to like come down now, yes? So there will be friction trying to oppose that. So that means your frictional force, rather than going in the same direction as the object, it will be trying to like drag the object downwards. So that means that it's not the entire frictional force that helps the object, the vehicle, to actually make a successful U-turn in when the road is banked. Is a component of it, because now since the road is banked, there's an angle involved, and anytime you have anything angle involved, it always tends to reduce the magnitude of each and every one of those components. It's like you're trying to apply your full force. You're trying to pull an object, you're not inclining your hand. The impact of the force will be reduced, will be diminished. But then if you apply the force directly in the same plane as the weight of the object, then you'll be able to like lift it more, and then you'll be able to like the force that you're applying will be maximum in that case. So since the stuff is inclined at an angle now, so the stuff will be very reduced. So these are the representation that you have. So this is what your angle theta. This is the banking angle, and then you have your normal reaction. Now you have the your weight of the object also coming down. Now the weight of the object is coming in this direction. the wake of the vehicle is coming this direction. Now, since you have a normal reaction, your normal reaction will also be inclined at an angle. Your frictional force should be inclined at an angle, because normally your frictional force should act downwards. It should act downwards along this plane. It should act downwards. Let me draw it here. Your frictional force should act like this. It should act like this in that direction. So now, with that now, I said net force along the vertical direction is 0, because obviously the object is not going upwards now. The object is moving on the horizontal plane. So and if the object starts to move in the vertical plane, then that means the object will start flying. And if the object starts flying, that means there won't be contact between the vehicle and the ground. So all this thing becomes very pointless at that point. So therefore, your n cos theta is equal to f sin theta. Looking at all this, for vertical, the vertical direction, net force in the vertical direction is 0. So that means your f n cos theta, which is this, is equal to what? F sin theta plus what? Mg sin theta. So they are using the vertical component as well too. So you have n cos theta. They said net force, so that means the resultant force there is 0. So that means your n force, the force going upwards, will be equal to total force coming downwards. And total force coming downwards is both what? The weight of the vehicle and then F sin theta. Because since the frictional force is inclined at an angle, something like this. Since frictional force, let me clear this. So you have the weight acting downwards. Now there will be frictional force. Now actually the frictional force is actually in this direction, but then just maintain that. And then there will be normal reaction. Normal reaction is always perpendicular to the surface, regardless of whatever reason. Now you have this. Now your frictional force, now since it's inclined at an angle now, this is the banking angle. Since it's inclined at an angle now, your frictional force is inclined at an angle, so it will have two components, the vertical and the horizontal. Same thing for your weight, so you have two components, the vertical and the horizontal. And the same thing for your normal reaction too, it has vertical and horizontal. So that's basically what they are saying there. Now basically they resolved each and every one of those forces into the vertical and the horizontal, vertical and the horizontal. So what you're not saying is that in the vertical direction, the net force is 0. So that means the sum of the upward forces will be equal to the sum of the downward forces from equilibrium of forces. So you have n cos theta equals f sin theta plus mg. Now they said the centripetal force is provided by what? The horizontal component of what? N and f. So that means mv square over r, which is your formula for calculating your centripetal force, will be equal to what? Formula for calculating the horizontal component of n and f, you have what? N sin theta plus what? F cos theta. So now you can substitute f with the frictional force with what? Nu n, because that's the formula for calculating what? Your frictional force. So you are going to have what? All this new set of formula, n cos theta equals to nu n sin theta plus mg, mv square over r equals n sin theta plus nu n cos theta. Now when you solve and every one of them, you are going to get what? Your v mass equals to what? Root rg tan theta. Now these are the few things I want you to like take note from this. When the stuff that are leveled angle, leveled root, you have v2 because it was square root of what? Nu rg. Now that the stuff is on bank road, you have what? It's thought to be what? Rg tan theta banked road. Take note of this. Tan theta is equal to what? Nu. So that means what? For banked road, nu is equal to what? Tan theta. Take note of that. So that the important stuff that you should actually take note of. I want to know these angles. I want to know all this. I want to know these formulas. That's basically these formulas. Let me now once you know all these formulas here, then you can make each and every one of them solve the formula depending on what you are being asked in your question. So that's all for circular motion. See you guys in class when we start solving questions and all.